how a graph look like. It contains vertex and edge and maybe weight also. And the edge may be no link or no direction or without direction. So in this case, you have concept about undirected graph or directed graph. Okay. So how to define graph? Okay, how to define? So you can see by this figure. So you can see the formal definition of graph is here. What does it mean? Graph consists of vertex, a set of V minus vertex, and a set of E we call the link or we call H. Okay, so graph E consists of two sets. For example, I give you for example A, B, C, D. If you have like this, or no, A, if you have like this, okay, then this graph we call undirected. And we call here directed graph. And how to define formula? We call the graph G defined by contain two sets set V. Okay, we call vertex and set E we call H. So set V consists of A, B, C, D. For set H we have AB. AB represent for B to A. Sorry, from A to B. Next, we have link from A to B, and this here undirected. So if in that we have B to A also. A to B and B to A. Order. We have A to C and C to A. You have B to C and C to B. You have B to D and D to B. You have C to D and D to C. Okay, you have here that is this set. How many links? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Corresponding to in figure you have 1, 2, 3, 4, 5. Because 5 multiplied 2 direction equal to 10. For this figure, graph G that equal to 2 set V mean that vertex, E mean that H, and set V equal to contain A, B, C, and D, right? A, B, C, D, and set E contain A to B. You had a row or link from A to B, not B to A. So otherwise you don't have any B to A. Next you have A to C, and next you have B to C, and next you have B to D. Represent 4 link. 1, 2, 3, 4. Correspond to 1, 2, 3, 4 link here. Okay. That is the formal definition for graph. So you can see for any graph you have the concept about the vertex and edge. And sometimes you have, for example, another. Let's see about you here in order. A, B. Let's talk about C. We also, and we have also D. And let's talk we have that is represent for let's talk about the cost between A to B. Let's say for 10, for example 12, for example 7, for example 6. Here the cost, some kind, right? I don't know what I mean, but in application that is some ways or some cost, maybe money, maybe time or so on, right? Or for the amount of bit rate or so on, right? Don't care about that right now. That depends on application. So let G equal to the two sets. V means not the vertex, and E that is the S. And V right now similar. We have A, B, C, D contain A, B, C, D. And E that equal contain first A to B with the cost 10, A to C with cost 12, B to C with cost 7, and B to D with cost 6. Okay. So in this case, you can see the edit information not only contain the start and the end, okay, or from and to, but also the weight information. Okay. That is a formal definition for graph. So you can see that is the concept about graph information. And next, I learn about the adjacent. What I mean adjacent? Please wait for me. So let's talk about the adjacent. Back to this graph. You have a link from A to B. It means that A net to B, B net to A, or A is adjacent of B, or B is adjacent of A. Or another concept, A is neighbor of B and B is neighbor of A. Okay, so there are some keywords here. Adjacent. Here. Or neighbor. Or net to. Okay. No. That is some keyword you can use in interchange. What I mean? Okay, we have one link one link from A to B. So A is the adjacent of B, or B is adjacent of A. But there is no link from A to D. It means that A is not neighbor of D, or A is not the adjacent to D. Okay. Here that is how you count links. But a little bit different for the rest. Here, you had a link from A to B, but not link from B to A. It means that B is a neighbor of A, but A is not neighbor of B. No, because we don't have the reverse link. Or we call B is adjacent to A, but not reverse. It means that A is not adjacent to B, because there is no link from B to A. Or B is net to A, but not reverse. Means that A is not the to B. It means that now you count about the link here, adjacent. So that is the concept about adjacent. Next here, for the concept about paths. Path is the sequence of adjacent nodes. Path is the sequence of or list of adjacent nodes. So what do I mean? For example, here you have a path. In this case, path A, B, sorry, A, B, D. Okay, A, B, D, C. Maybe like that. Okay. Here you have a path in the graph. You have A, B, sorry, A, B, D. But you don't have any path D, B, A. No, because we don't have the reverse direction. Okay. That is a path. The cycle is a path contain at least 3 vertices, but the start it is the same to the end of that path. What do I mean? Here is cycle. Here is cycle. Here is cycle. Or maybe around here also the cycle. So you can see A, B, D, C. Okay, that is also a cycle. Or B, B, C also a cycle, right? Let's talk about for this graph. You have A, B, C. A, B, C not a cycle. Why? Because here you can see A to B, B to C, but there is no link from C to A. So that is here is not a cycle. Not a cycle. Again, I want to emphasize A, B, C. Not gọi là this. Yeah. Okay, sorry. It's not a cycle. Or sometimes we call not a ring. Not a ring, right? Again, not a ring. But in this case, I think that you have another graph. You have A, you go to B, and you go to C, and you go to D, and you go to A again. Here cycle, or maybe you have another. Okay, don't care about that. So here is circle. Because you have the circle is the part A, B, C. A, B, C, D. So you can see now you go next to the A. So that is the cycle. One next here. About connected. Connected. What do I mean connected? Here. No. Question. Here. For example, here a graph. We can't connect it. Hello? Are you there?
Yes.
There is some problem. Can you see it right now?
Yes, sir.
Well, I cannot see anymore here. I want to show it. I don't know why. Please wait because I cannot show the application. I don't know. I want to quit it. 4. Can you see here what I mean? No. Just allow and so on. I can solve. Please wait for me some minute. I had to confess and show the at the top. Badminton. Hello, are you there? Hello? Can you see my laptop? Hello?
Yes.
Okay, we continue. So I talked to you about a circle. So I think that is the almost of information of the concept about graph already presented. About the definition of the graph, about the concept about adjacent, neighbor, and net two. About a circle. Okay. Before we go to the how to element, I want to introduce about the API should be provided by graph data structure. Okay. Why is no. Please wait for some minute. So now I want to introduce about API. Here. Can you see? Hello.
Yes.
So you can see that it similar to the list, heap, sort, in every data structure. My design, I always define the interface. It contains, for example, iGraph here, it contains the API should be provided for data structure, graph data structure. So let's talk about T. T is the vertex user data for vertex. Why? Because now we are developing the graph data structure. We don't know in future what kind of data structure the user pass into the vertex. Maybe integer, maybe string, or maybe object. So that's why UT. So remember T is the vertex data of user. So here you had a method for add. add to the meaning of add is to add the vertex into graph. To build, in order to build graph, you add many vertex inside, and then you connect between two vertex. From vertex, from and to. So we call icon from to. So that is quite difficult for understanding. So I come from F means not from, T means not the to. So from F to T means not from start to end, right? And sometimes if you want to connect, and when you want to specify the ways, you also pass the way here. So add and connect. But sometimes you want to remove vertex. So that's why that is vertex here, remove vertex. And sometimes you want to remove link, or we remove S, so that it connects. Sometimes you want to reach the ways of the vertex of the S only, so that is the ways. And sometimes you want to, if you want to check whether the graph contains a vertex or not, so that is the content, the meaning content. If it turn true, means that the content, not the default. Okay. And the sign means that the number of vertex inside of graph. And now, next I want to explain about in degree and out degree. Okay. Go to the back to the graph here. Assume that you have graph like this. A, B, C, D. And another we have A, B, D, C. Here that is the ungraphed, undirected. That is directed. Now talk about the in degree and out degree. We have V vertex. In degree, out degree. A, B, C, D. We vertex. In degree, out degree. A, B, C, and D. Now, how about to fill the in degree and out degree? For the vertex, you circle around it. And you count how many links go out. We call out degree. For example, in this case, one link go out from A to B. So that's why you count here is one. And you count how many links go in. In this case, only one link from B to A. So that's why you see one. And similar for B, you make a circle and you count how many in and how many out for inside go in. You have A to B, C to B, D to B. So that's why you have three in. And similar go out, you also have three out. So there is three out. And similar you count for C is 1, 1, and D is 1, 1. That is for directed graph, undirected. So you can see for undirected graph, the in degree and out degree only the same. The same. But how about for directed graph? Level circle around A, you count how many in? No in, because there is no link from A to B, from outside of to A. Let's talk about waiting for me a minute. So you can see, you count how many in? No, because you had a 1A to B, not B to A, so that's why that is equal to 0. But out, you have count how many out? 1, because we had A to B, so that is 1. And similar, you count for B. How many in? 1 in, because A to B. Okay. So 1 here. How many out? You had 2 out from B to D and B to C, 32. And similar, you count for C, that is no out, but 1 in. 40, no out, but 1 in. And for example, here you can see in degree and out degree. Right now here is different. Okay, for in degree and out degree for the rotor prop. So back to the ABI. That is the meaning of in degree and out degree. You query with the vertex. For example, here, given the rotor prop, you query for B with in degree return 1, but out degree return 2. Okay. For inward and outward, given one vertex inward and outward, what do I mean? For example, inward from A, mean that from outside going inward. You can see inward. You have one in this graph. Inward contain only inward for A, E contain B only, and outward contain only B. So now for B, inward equal inward to B, mean that A to B, so that is the inward A. C to B, mean that inward also C contain C, and D to B, mean that inward contain D. So for B, the inward contain A, B, A, C, D. And how about our the same? Because from D, B to A, B to D, and B to C. So that is, if you query for this graph, you query the in degree, inward, you return A, C, and D. That is the list contain A, C, D. And outward, you contain also A, C, D. But for this graph, when you query with the node B or vertex B, inward contain only the list contain only A. Outward it contain D, C, and D. Okay, no A. That's why the meaning of here it return list contain the vertex. Okay, for inward and outward in this case. How about iterator? It look like the list and the heap or so on, right? That is the provide the way to travel on drop data structure. Okay. Okay. Any question for me about the ABI of iGraph? Hello. Any question? Hello. Is it clear?
Yes.
Right. Want to see what I mean this. Now we go to next. How to element. Okay, let's talk about now. I want to view only, right? I want to introduce about how to element. That is my element, the way I element this. I have interface called iGraph. Hello, can you see here? I have interface graph. I element by that is we call the abstract graph. And here we have another we call the You have at least 4 ABI, 4 interface and graph. You have link here implementation. And here user or at 10. Here is or at 10. Here the interface. What I mean, in our implementation, I have 3 class and one interface. I only present about iGraph contain the API or define the meaning of the or semantic of the API only for graph. And now for implementation, so you have to create class, and one class we call the U graph model, or we call indirected graph. And another class we call the D graph is represent for directed graph, D graph model. And each attempt from the abstract graph here class, and each element the I graph. Why I had to element like that? Because let's say we have around here we have some API in iGraph here 3, 7, 10, about 13, 14 API. Yeah, 14. But some of them can be shared between 2 kind of graph. Some of them can be shared. I mean that if you want to element, you can use the same code, so that we can be shared. So that's why I create the abstract class to contain the share, the container method can be shared. Okay. Here, this contain, we call it common code. For U graph model and D graph model. Common code. But some of method you cannot be shared. Even that the implementation are different for the directed graph and indirected graph. So that's why you put the code inside here. Okay. It means that it contain only code. For undirected only. And here the same, similar, contain code for directed graph only. Is there any question about my design in OOP? Object Agile, the object oriented programming. That is. Hello, any question about it? Hello? Is it clear? Can you hear me?
Yes.
Right. So in the morning, some students asked me that why I don't direct element undirected graph element iGraph and directed graph element iGraph. I told you that if you do like that, then you repeat code for common here. You have to repeat code. Otherwise, not good, right? You go to the code, you can see. I D graph model means that the U graph model means that the undirected. Open it. And you also have abstract also. My machine recently is very slow. Yeah. So you can see here graph abstract. You can see here what I mean. Here, implement I graph, right? That is implement interface. And G graph, you add 10 abstract only. And D graph, you add 10 abstract only. Right? Okay, that is the way to implement. And now next, the question is how to use it first, right? How to use. Let's talk about. Now I want to create this. I show you how the API how to use. Here, I want to create this graph. And this graph. So how to use? One here. The graph. I go to graph demo here. Comment it. For ABCD, let's talk about ABCD first, right? U graph. Okay, without undirected, let's talk about here. I create graph model. Here is graph object. As in we have vertex A, B, C. So I ask here A, B, C, D. A, B, C, D. There are 4 vertices. Add in 4 vertices. As you can use for loop. You can define the array of contain the vertex A, B, C, D, and then you follow to add very simple. And now for connect, you connect AB, BC, and DC. Okay, how to you connect AB, falling. Falling, you can see a trillion only, right? AB, BC, BC, and BD. Remember your code is you add the AB, BC, AD. It means that you can see here only 3 lines, and then you add it 3 lines, and you print in. Okay, let's talk about it like that. Okay, you can see what happened. Waiting. Okay, you can see now you had the here the printing for graph from here to here. You can read it. Vertex equal vertex A, B, C, D, right? A, B, C, D. In degree and out degree 1, 1, right? 3, 3, 1, 1. You can see the same here. And for the S, okay, let's talk about it. In your code, you only specify the A to B. But actually, for the unrelated, when you add A to B, it means that you also handling B to A. Again, for unrelated graph, when you add AB, it means that you also have B to A. So here, AB and BA. You add BC and then CB also. You add BD and then DB also. And then by default, the weight is 0, means that you don't try to specify the weight. So that way, by default is 0. Okay, that is the information from graph. But how about if I copy the same? But here for the graph, you can see A, B, C, and I copy here. It means that for D means that the directors, you can see the directors here. A, B, B, C. You have A, B, yeah. A to B, B to C, and B to D, 3 links, right? And then now I use the modi comment. I use it. I run it. Now you can see here. Similar, you had 4 vertices A, B, C, D, A, B, C, D, and in degree right now is 0 and out degree 1. You can see the same here. For B, in degree 1 and out degree 2. You can see, and similar for D and C, C and D. And for the S also different to the unrelated. Now you have 3 S only. F from A to B, not B to A. Right? B to C and B to D. By default, the code cost the weight is 0. So, okay. By those demonstration, I told you how to build by our library, how to build graph. Again, let's talk about I use D graph. And then double then T. T right now is it dot. The vertex type right now is string. Okay, string. Again, because we can use the generalist, right? Means so that's why you can pass any kind of the data type for vertex, not only string, maybe object, depend on you. Okay, and very simple. Here is code for symbol, but for industry code, I think that is you should you can create an array of vertex, and then you can create a pair of vertex, and you can use for loop, and then easy to build a graph. Right? Very short. Don't try to very long like this. Right? You follow. Hello. Any question about how to use our library? Is it clear? Hello. Is it clear?
Yes.
There's no question, right? Again, if you have question, just raise your hand, or maybe you ask me directly by speech with microphone, or you can try to type the question here. You can put the question here also. Okay. Now go back. Now let's talk about how to element. Okay, we are able to use it, but how to element? There are several ways. There are several ways to element. First, we call the concept is adjacency table. When talking about adjacency table, it means that I use the memory that is the 2D array. Right? Remember that is continuous memory. It means that you can see the 2D array data is all of data here is organized continuously in 1D, right? But we reset into 2D, but that is continuous. Let's talk about how about the graph. You have 4 vertices called 0, 1, 2, 3. So you had a vertex list 1, 2, 3, and you also have the table. Contain what? Contain the mapping or contain the indication of the vertex. For example, the row here is represent for vertex, and the column also the vertex. What I mean, the meaning from row to column. Row, column. It means that equal to link or edge between. That equal to 2. It means that the edge from row to column. What I mean? Let's talk about here 2. Row is 0, is 1. In column is 2. What I mean, we have one S from 1 to 2. From 1 to 2. You can check here. From 1 to 2, this S. And what do I mean about that is font? Similar, that is font. What I mean, that is font. Row right now is 2, column is 0. It means that from there is no S from vertex 2 to vertex 0. Vertex 2 to vertex 0, no S. But one S from 0 to 2. Let's talk about from 0 to 2. Okay, there one S. So you can use the 2D array to identify there are a link or the S between any pair of vertex. That is the one way to do. We call adjacent table. So how about the memory? If you create a table like that, and if you have n vertex, then the table here we have n row and n column. How many items inside? N row and n column. How many items? N square. The memory is big O of n square. Okay. But that way, it's really fast. It's really fast to answer. Is there any link between one S to one vertex to another vertex? Because you can use random accessing. Let's talk about I pass row from row 3 to 2. Now you can see 2 there is a link from 3 to 2. You can answer very fast by random accessing. But memory not good. Okay. So about here the pseudocode you can convert to Java by yourself. So that we call adjacency table. Here, similar, but right now you have not only identify there are a link or not link, but also the ways how to store ways. Similar. Here you have A, B, C to F. You have the vertex here, vertex list you have A, B, C to F. Then row right now you have row is also corresponding to the vertex. Column also corresponding to vertex. And similar, you have n square item. And right now, for example, from A to B with the cost, the way right now is 623. So A to B 623. But because this is the unrated, so you also have a link between B to A. So B to A here. Also, the cost is 623. So here, because here is the unrated, so you can see, you can check B to D here, 548. And sure, you also had a one link between D to B here, the same cost. So you can see that matrix is symmetric. That matrix is symmetric because it is undirected. Here, the way to use the also adjacent table for weighted graph. Okay. So if the weighted graph but that is directed, so you might be not symmetric because this is symmetric because this graph is undirected. So how pseudocode? Here is pseudocode. You can convert to Java by yourself. Here the way to use the table. And again, to be evaluated, the memory complexity is n square. But in order to look up the link or to get the ways very fast because that is just random accessing, just constant time. Or maybe you can use the adjacent list, not adjacent table. You have two kinds of lists. We call here vertical list, one vertical list. That equal the list of vertex. So it means that you have here A, B, C, D, E, F. So you put here the list. You don't care about the order. Okay. The list maybe you use already or list, I don't care, right? But here the list. And how about the horizontal list? What I mean B. B that is list horizontal. You attach to A. It means that you have the link from A to B. AB. Here also you have AC. It means that from A you have two links, link to A and link to C. Here A to B and A to C. Again, this nodes contain one link, one link list. Contain that list contain BC only. We call the adjacent list. Here also adjacent list. So you can see, for example, D, very long here. You have link between from D to B, D to C, D to E, and D to F. You can check it. 4 link correspond here. And the number here contain ways. Right? Okay, that is the way we call the adjacent list. And you can verify you have AB and BA, AB and BA, so you can see that is duplicate the value here. You have BD and DB, BD here, and DB here, so on duplicate across. We got a directed graph. Hello. So the at least I only tell you about adjacent table or adjacent list. And now go to this picture. This picture a little bit complicated, but I select it. I select this, okay. Here, what I mean, we had one list similar. Here contain the list of vertex. And horizontal here, list of add information. So I introduce, in this case, you introduce two kind of objects, two kind of class. Here and here. Here we call the vertex node object. And here we call the S node object or S object. So vertex, sure, the vertex it contains the vertex, the user data. Remember what does mean vertex and vertex node. For user of prop library, they just know about list the vertex only. Know the vertex, their data, but they don't know about or did not to know about the accepting of vertex node. It means that vertex node is the your class. You create this class to support the implementation. The user need not to know, but the user only know about the vertex only. And similar here for the add information, you create the add information. We call add or add node. In our I use add, not add node. Hello. Hello, can you hear me? Hello. Maybe had problem again. because it disconnect about this software. I hope it's so here. Okay, thank it disconnect. So again, I want to emphasize the user, they don't know about vertex node or edge information. They just know about the vertex, their data. So that's why here, in order to element, I select this for my implementation. I talk about it. Here you can see I create one class called vertex node. Again, the user of our library, they need not to know about it. And vertex node contain vertex sure, and also in degree and out degree, and also adjacent list. What do I mean adjacent list here? Here. For vertex nodes of node 0 here. Here is vertex nodes. Here is the adjacent list. So if not, this is a linked list or array, I don't care. But that list is contain adjacent, mean that you have 0 to 1, 0 to 2 here. Yes. So let's talk about this implementation. You have that is adjacent list. And how about the edge? You have also the edge node or edge. F, you had a one node we call from or start, or we call node F. F stand for from, and T means not for two. So we contain two reference, one to from and one to two, and also the ways. Okay, and the way. Okay, that is the data structure for S node and vertex node. Okay. Now I want to explain detail about how implementation. Any question for me before I go to detail? Hello? Any question? Hello? No? Right? Now I go to detail. Let's talk about implementation. I told you that I use object graph to contain a common code. So go to the detail. Here, method S that it can be shared with a common code for U and D graph. U means not undirected and D means not directed. Contain also can be shared. Ways you get the way also can be shared. Over in one side in degree in the out degree print to string also they can be shared. Share on. Accept cannot be shared. The behavior of remove can be different for remove node, can be different for vertex undirected and directed graph. So that is, I put here the graph abstract means that not implemented yet or unimplemented. And similar for connect and behavior connect and disconnect also. So that's why for you can see in view graph, you element only the methods not shared or not common. The connect, disconnect, and remove. Right? And see for directed also. You element for connect, disconnect, and remove. Right? So that is about you had a picture, the whole picture about how the code organized. Remember, I want to emphasize again, abstract graph contain a common code for two kinds of graph. So go to the detail about adding. how to eliminate adding in a graph. So let's talk about how data first. Here, I use the node list to contain the list of the vertex inside or vertex node. What do I mean? I want to clarify for this elimination. Assume that I want to remove for this graph A, go to B, go to C, and go to D. That is Dưới graph model, right? Dưới in the graph. Now how about adding? So back to our elimination. I use one list to contain the vertex. So that is that list. We call node list. You contain what? Assume that I use the polling list. So that is picture like that. The polling list A, B, C, D. So here node A, node B, node C, node D. So whenever you ask enough for vertex, then that is the figure of node list. Here the figure of node list. Again, here is vertex nodes. I want to emphasize here. Vertex node object. Here the picture. Vertex node of type T. T means that the user data. So the object graph contain the node list. That is the projected. What I mean, it can be accessed by the children. It means that can be accessed by Dưới graph and D graph. So for adding, simple. The user pass the vertex data, for example string. I create the object vertex node by new, and then I pass into the add method of the list. Remember, add here is the add method of list data structure. Here, you can search the API for list. Okay, you already learned. You can see that is the add. So very simple for adding. I add into the list. So after adding 4 times, for A, B, C, D, you get this picture of here, the picture of node list. Okay. Now how about? Okay, so let's talk about here. For the graph, I don't know why the mouse is automatic moving. Here you can see the graph A, B, C, D. After adding 4, you get that. And now I think how about connect? Talking about how connect A to B. How connect A to B? Go to abstract graph. The connect is the abstract, right? It means that here should be eliminated for D graph and Dưới graph different. Because the behavior of them are different for 2 kind of graph. Let's talk about D graph or Dưới graph. How to connect? Here, right? You connect this. How to? Here in general, okay, I discussed about it. The user pass not F mean not from, not T mean not to, mean not from to, right? From to. With the way how to do. The first two line to get the reference to vertex node. This API to get the vertex reference of vertex node, maybe null, return null. So back to here. Here. What I mean, how do you implement this? Because the user pass the vertex you search for the vertex node, it means that you search the vertex node in this list. You go from beginning to the end, you search for the node contain the vertex. For example, if you given the node B, a vertex B, you return reference to this node. So that's the idea. But if the user pass, for example, node F, you return null because no node like that. Okay, so that's why you use the while loop. You search for the while loop with the here. Remember here because you use the linked list, double linked list, so that's why that is take time. So I think that is you can improve by using the hard map and here because hard map can be accessed to the node very fast. As simple, if you have let's say about 10 million of nodes, then this library can be run very slowly because this while you search with linear time, so slowly. Okay. Right now you have a lot of data structure can help you to provide the log to n. Okay, better for example binary structure or maybe random for example array list. Okay. Or maybe the hard map. I think better the hard map be better. Okay. So already one implementation from you better. I recommend you to improve. Let's talk about it. Continue. So the next two line here verify if the node null. It means that the user want to connect from two vertex, but the vertex is not accepting. So that's why you have to signal the exception. That's why simple. And here it means that if the both F node and T node accepting, then you have to perform adding. What I mean, you can't connect from vertex node. You can't hear the connect from graph, but here the connect from vertex node. Okay, you connect from node T to node F, connect to node T, and node T connect to node F. So that's why I told you that. So that's why for unrelated, the user only passing the adding from A to B, then it automatic adding B to A. As I told you before. Here, the user add only A to B, but it also automatic to add B to A by two line here. Right? But compared to the graph, similar. The code quite similar. If acid, you can see that you search for graph node, the vertex node, and if acid, then you can see the user adding from F to T. Then you only add from F to T only. You don't try look like the behavior here for U graph connect A F to T and T to F, right? For the graph, it's just one link, one way. So that's why okay, you can see why different the behavior. You cannot be shared. You should separate it into two classes. Okay, behavior different. And now you can see the connect from the graph, it can't connect from vertex node. So that's why we have to open vertex node and you can see what happened. Vertex node here. Connect here. What do I mean? Here. The idea of how to connect, let's talk here. The user pass the node to node T and wait. Remember where I know F because no F store here only. Again, because you can't connect on node, so it means that the node, the from only store in this only. The here is from, here is to. Again, because you can't connect on vertical node, so from only store at member variable. And T2 means that you store here. So otherwise, you can search for, remember the vertical node contain the adjacent list. So that's why you can search for what? The S. Okay, so you can get S. What does it mean get S? Return S information. Here is the adjacent list. You search for the S. If you search for the object here, or here, or here, or here, right? How to search? Because you only had a node. For example, node from means that this node. So this node contains one adjacent list, that list. So it compare only node 2. Okay, if node 2 equal to the user passing and you return. I think a symbol if you pass node 2 equal to 2, it return this object. That is the idea. That is the idea. So back to the code, you can see that is the idea of get S object. It return the S reference to S. If null and not null. If not null means that the S only existing. You just update the way to new ways here. If not exist, you add. So let's talk about not exist. Now I go to demo. You connect A to B. Let's talk about how to. You connect A to B. A to B. So you can see we have two links. You connect A to B. It means that inside the code, you reach to the node A. You get the link here. Here is adjacent list. Now it's null, right? Now it's null. Now it's null. Here by default here is null. But after this line, here, you should for node from now from EA, FEA, TEB. So you execute it first. A you connect to B on this chain. You access to this, right? This. So now it's null. So if when you shoot the S, no S return because that is null right now. So that's why when return you create the node S. You contain the one S node, look like here. S node contain several information. I tell you about it. How the S contain information. S contain link to F, link to T, and way. Okay, three information here. Let's talk about three information. So here three information. The first is go to node F. So node F right now here is A. So it go back to A. Node T right now go to B. It go to T. And way now equal 0. Okay, remember here is list now it contain only one item. So again here is node F, here is node T, here is way. Okay, so that is when you call this API, then you call API, it create the picture like this here. So adjacent list contain one S information, one S object, it contains A here, go to B. And one net line, it contains not T to not F, not T right now EB, not F now EA. It means that, what do I mean? Not T right now EB. So it go to this, not T now EB. It accept the adjacent need to not B. So not B now empty. So it search for now empty. So you add one T to A, B to A. How to add B to A? Sorry. It contains here three part. Part F, part T, part W. W now equal to 0. 0, right? So how about F? F right now here you go to B. Because that is F means that from B to A. Here go to A. A little bit complicated, but like that. Again, here is 0. Here is 0. Okay, you done. Go next. For example, you add B to C. How got B to C? Again, B to C, because that is in the graph. So when you connect B to C, so B right now is F, T right now F, not the F be B, C is T. Again, the user add to add B, mean that from F, C, T, mean that the T is C. So you can see you add B to C and C to B, and similar. You can roll out it. For B to C, first B to C. B to C. It means that you read to that object B, and that you accept to a adjacent list, you add one edge information. I think that is double in it. Paper. That is equal to 0. And you fill B to C, so that is not F, now we go back to the B. Right? Not F. And not T. Not T right now also go to C. Okay, not T. That is B to C. And C to B. C to B is similar. You read to the asset not C to B, so you read to the node adjacent node not C. Here empty. So now you remove it like that. You add one edge information. So node F, that is 0, right? F right now we go back to C. And T right now we go to B. F and T. Okay. So that's why you can see B to C, B to C, and C to B. Okay. So right now that is the way to perform adding or connect. But remember, for connect, after you connect, you also change the out degree and in degree corresponding. For example, if you add you perform adding B to C. B to C means that out degree go out from B, so means that out degree of B go increasing 1, and in degree of C go to 1, increasing 1. Okay, you have to maintain here. Okay, I already planned how to perform connect, add, rotate, and connect. Any question for me? Is it clear? Hello? Hello? Is it clear? Are you there? Hello, are you there? Is it clear?
Yes.
Cannot see anything. Okay. No. I don't forgot. I decided to teach the hot map after graph because now you had a motivation about using hot map, the concept only, and then next after we study graph, we learn about how to implement the hot map. Any question more? Is it clear? Any question? Is it clear? No, right? If no, I know. Okay, I tell you about how to implement the net method, the removal. Remember in abstract class, abstract graph, you don't have any implementation for remove because the behavior also different for U graph and D graph. So let's talk about for behavior. Here. For here, removal. Here, remove node. What do I mean? For U graph first, let's talk about the first. The user want to remove the vertex, so you have to access to the vertex node. Not null, you should know the exception because user want to return to remove node F, but node F is not exist, so that's why you have to know the exception. If the inside you have to perform two tasks, task 1 and task 2. Let's talk about why task 1 you had a for loop, right? Let's talk about this. Here, a symbol if you want to remove node B. You want to remove node B, okay, here. Not simple try to remove B from the node list. Don't try to do like that. Why? Because if you do like that, then after removal, the add information here go to B is invalid because B now is have been gone or have been removed. What do I mean? When you want to remove node B, it's not easy to remove node B from node list because B can contain in the order reference. Let's say, for example, this object in a lot. So let's talk about how to. You have to remove on of the link. Okay, on of the link. Here, now filling. Go in or go out, especially go in, not B. Here. Let's see about you have to remove this link, this object, because the object has not T equal to B. Here, not T also equal to B, so remove. Okay. So you have to remove this node and this node, this link and this link. If in that, this link to A, this link to C, and this link to D also. Okay, another D also. If you have D also, if you had to add D, then also you have to remove link from D to B also. Here, that is the purpose of that course. To use the follow on what? On node list. It means that for each node in node list, you get the nodes, the edge go to vertex. And if like that, you perform removal. Here, removal. What do I mean removal? You remove because for unrelated here, unrelated. So that's why for adding, you add in two way. For example, when adding A to B, you also add B to A. So that's why you have to remove F to T and T to F. Okay. So again, the purpose of this code is for removal on of the S go to B. After that simple. After that is you just remove not B from not list here. You just remove not B from not list, simple. Okay. Is it clear? Any question for me? How to remove a node, right? Any question? It's easy, right? No question. So if you don't have a question, go to net about removal for similar for the graph. That's similar. You have to check that is the vertex node is acid or not. If not, you have to signal the exception. And you follow the similar to remove, right? For removal. On of the link go to the node C. And after that, you remove it. The similar. Hello, any question? Hello. So for the routed graph is similar. You have to do the similar. Any question? Hey, hello. So how about the connect for removing? Here the connect. So you can see the disconnect here is the behavior also different for U graph and D graph. So I here disconnect. For D graph here. If the user want to disconnect from T, from F to T, F minus from and T minus to, the code here to verify the node acid or not. If not, you have to throw exception. And here the similar when the S acid is it doesn't mean that the S acid, so that's why you check the S acid or not. If not, you throw exception. And after that, if acid for the S, you have to remove. Remember for U graph, in order to perform adding, you add two way A to B and B to A. So that's why now you have to remove also both way. F to T and T to F removal. But for D graph, similar, but now for you just remove from F to T only. That is all. Hello. So I only plan on of method here. Okay, important. On of important method for this. For it only. For the get in degree and out degree, I think that is simple because just look up and the return only. Okay. Hello. Any question for me? Hello. We need the 1 or 2 minutes to record about implementation. If not, we go to the next topic because I only complete and I only know about implementation for graph data structure. Any question? Hello, are you there? Quên, are you there, Quang?
Yes.
Any question? Is it clear?
Yeah, it's clear with me.
Okay, thank you. Dương Thành Công, are you there? Hello.
Yes. Yes, I'm here. It is clear.
Okay. So again, I want you to, let's say, I want you to element on of all the methods here. Because for adding, removing, the connect, okay, that is the most important and very difficult. I only plan. And I want you to remember this figure. I use this kind of data structure here. This figure, or maybe here. So I summarize about the most important. I use one vertical list here contain node, on of node. So when you add into this. But horizontal list here contain the add information. Each of item here is the S. And for remember, for undirected, you add both way, A to B and B to A, F to T and T to F. But for directed, you only add one time only. So that way, when you add two way, you remove two way. When you add F to T and T to F, you also remove F to T and T to F. And whenever to add in, you increase the in degree and out degree, you update. And when you remove, you also have to update the in degree and out degree. That is the way. For checking the for example about let's talk about the in degree and out degree. Similar, easy because you can pick up directly from the node vertex node here, right? And how about inward and outward? Simple. Let's talk about inward and outward. Okay, if I give you a node B, how about outward? Outward means that you return the list, this list horizontal here, or adjacent to be here, that we call outward. But for inward, if I give you node B, for inward, you have to scan on all the nodes, and then for it, you have to scan the horizontal, and then you check the inward to be. Inward, is there any list to be? So that is outward very cheap, but inward very expensive. Outward very cheap because when you access to vertex node, and then you get adjacent node, adjacent list, and you return. But inward, you have to scan on of the node vertical. And for each node, you have to scan on of the vertex horizontal. And for each of the add information you compare, it go to B or not, if go to B, you are return. You add, you append to result and return. So that's why how to read, to add inward and outward here. In degree and out degree is simple, right? How about outward? Outward very cheap, right? Very cheap. You get the outward from node. But for inward, you have to use for two loop. The outer loop here is for the node in node list. Then the inner node here is the S in adjacent list. Sorry, a little bit expensive. Please wait for me. Hello? Are you there? Hello? I'm busy a bit. Hello, are you there? Ooh. Hi. Okay. Now we go to the next topic on the. Okay. Sorry. Here. So you can see I introduce about how to implement a lot of method right now, right? Here just for reference. Here just for Reup, traversal, deficit, and preference. I already introduced in the tree, but now the principle the same, so need not to resent that. It means that you can use the implementation from stuck and queue for default and preface, right? In the tree data structure, okay, the same in graph, okay. So now next topic is the topological order. Hello, are you there? Can you see? Can you hear me? Hello.
Yeah, teacher.
Okay. What I mean, I want to explain what it means topological order and its application. Let's talk about we had. Assume that we had graph like that. Assume that we want in our system, if you want to develop a software to perform tasks, we had a list of tasks right now. A, B, C, D, E, F. Okay, C, E, not F. We have 5 tasks or 5 jobs. But what I mean the graph, now the dependency. If you have, for example, right now you have A to B, what does it mean? The meaning right now here is the task B, task A must be done or must be completed before task B should be done or can be started. The meaning B, what I mean, A must be done. Hello. Hello, are you there? I'm so busy. Hello.
Yeah.
Yeah, we continue. Sorry. So I think that we had this graph contain 5 tasks, and what the meaning? I want to plan the meaning of this graph. I assume that okay, that is A to B, mean that the A must be done, mean that the task B must be accomplished before B started. Able to be started. What I mean? Okay, you can see A to B must be done first. Okay, anyone here, you are able to review the CVB language? Hello, anyone here? If you are able to use the C++ programming, you can see in C++ in order to compile the big project, you have to build look like this graph. For example, you had a moon A must be compiled before B can be compiled successfully, and B in this case B able to complete and then able to compile successfully, and then you can continue with compile D and so on. So that's why a lot of application like that. So it means that can you tell me, can you execute task E at the first? No, right? Because A task E depend on C. So that's why C must be done first. So that's why okay, you have to perform, you have to convert the non-linear data structure, that is graph, into the linear data. It means that you have to perform, we call it linearization. What I mean, for example, right here, you can A, you B, you D, you C, you E. If you convert like that, you can see you have A to B, A to B. You have B to D, you have B to D. B to C, okay, B to C. You have D to C, D to C. You have C to E, C to E. You can see in this sequence, in this order, on of the arrow from left to right. On of arrow from left to right. Can see? Is it okay? So if on of arrow, if in that you sort the node or the vertex into the linear order, like this, and if like this, then we call it turbo order or topological order. What I mean, on of arrow or on of the dependency on one way only, maybe from right to left or left to right. Okay, well in this way that is left to right. And if you are able to sort like that, then in order to perform very simple, you perform test A and test B and then test D and then test C and then test E. Simple. You can compare A and then compare B and then compare D and then compare C and then compare E. That is very simple. Okay, that is the application of topological order. So topological order is the linear data structure. Okay, that is list of vertex. And in this list, on of the vertex must be ordered in one way from left to right or right to left only. In this way, that is left to right. That is topological order. Application, I told you that a lot. Any question about topological order? Hello? Any question? Hello? If you don't have any question, I told you about how to perform sorting with topological order. Again, I want to emphasize again, the topological order can be applied with derivatives. can be applied or can be produced, not applied. Can be produced from derivatives graph without cycle. Derivative graph without cycle, or we call dust. That means dust derivative. A cyclic graph. Another concept, that means that derivative. A cyclic graph means that the derivative graph without cycle. So again, topological order can be produced from the dot only. It means that without cycle, right? Again. So let's talk about how to let's talk about here. You have 1, 0, 1, 2, and 2, 9 meter and 9 vertex and link. And if you apply the topological order, you get this. You can see on or row from left to right now. Okay, left to right only. The question is how to get it. How to get it? Let's talk about it. I told you how to use it first. Hello. Are you there?
Yes.
Can you attend with me about 30 minutes more?
Okay, teacher.
Okay. So let's talk about this. How to use first. For example, here I can the topological order. Here, this codes for creating the graph, right? Again, you have 10 nodes from 0 to 9. Note and link. So here that is the code for adding to build the derivative graph. And in order to perform topological order, to create the software, you pack the model minus graph inside of the constructor here. And then the software dot sort with the mode. By default, if you don't specify that first, then that is you can use by default that first. And then you get the result here, the list of vertex. Remember, vertex right now here character. So you had a list of vertex, and you print out. Then you can see how to use. Let's see. Here. Here. You had a vertex, right, from 0 to 9. That is the edge, right? And now that is the sequence here. That is the result of the topo order. And how to check that the topo order or not? You just draw the link between any node here. Yeah, right? And then you can see all of the link or arrow from left to right. Okay. The question is how to do like this. Okay, I tell you how to do. Because you can have a list only, but the question is how to. We go to the code. Before we go to the topological order, I deal about the stock and queue. Here, I element stock and queue using linked list. In this class, in topological order, you have two ways to do. That is default and preface. I want to plan for preface. Okay, the step by step here. Step by step. Because I have to return the list of the vertex, so I have to declare the vertex variable. That is the linked list. By the end, I return it. Right? And now let's talk about list of zero in degree. Let's talk about list of zero in degree. Here, you can see the zero in degree. Zero in degree. You can verify and you put the list here. Any you scan from vertex to vertex and you count. You count the in degree and then you put to the list here only the vertex with in degree equal to zero. So let's say about here. You have 1 in, here 2 in, here 3 in, here 0 in. So right here not 3. Now next, not 4, 2 in, not 5, 1 in, not 6, 0 in. So here 6. Not 7, 3 in, not here 2 in, not here 0 in. Okay, not 9, also 0 in. Let's talk about hard map. The hard map you learn in the after the graph. What I mean, that is the data structure to map from vertex to in degree. Look at the table. Lookup table. So you have here the vertex in degree. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. You divide into block of 3. Now you fill the in degree for here. You count. Not 0 in degree equal to 1 because 1 in. Not 1. Sorry. Not 1 you have 2 because of 2 in. Not 3 you have 3 in. Not 2, 3 in. Yeah. Not 3, 0 in. Not 4, similar, 2. Not 5, 1. Not 6, 0. Not 7, 3. Not 8, 2. Not 9, 0. So you can see here, marking here 0 for not 3. Not 6, and not 9, you can see that is equal to here. And net about breakfast, what I mean, why we call breakfast, we talk about we use khiếu here. The two line here, you put the khiếu contain on the khiếu contain on of the vertex with in degree equal to 0. In degree equal to 0, okay, in degree 0. Again, queue, you design the queue will contain a node which in degree equal to 0. So right now, back to here, you create a queue like that. Now you contain in degree equal to 0 right now is 3, 6, 9, maybe 3, 6, 9. But the order 6, 9, 3 on 9, 3, 6, okay, depend on how to order, right? So again, when you perform, let's say about final examination, I'll tell you about the convention about how to order the vertex inside of the queue. Maybe increasing, maybe 3, 6, 9, or maybe decreasing 9, 6, 3, so on, right? So you have to focus on that. Now I put it 3, 6, 9. So you go to the follow. While loop. When you finish, when the queue empty, you finish. When the queue empty, you finish, and you return to topological. And now back to the topological, that is result. Okay, that is result. Result right now empty. I put here. Now back to the code, you do the while loop. You can see simple to remember. Here you pop or you remove. You pop from queue. You put to the topological order. You move the from queue to the result. Okay, the result. Here result. The first, the net. You get a neighbor our list. Our mean that from that node mean that node go outside, go over. We call neighbor. And then for each neighbor, the tree line here, you update the in degree by subtract 1, and when it go to 0, you put it to the queue. Remember, when it go to 0, you put it to the queue. Even they compare 1, but the 1 is before I degree. Before I degree 1, so after it must be 0. So here is for each neighbor, you update the hard map and you put to the queue. After that, you go back to the while loop. So stable here. I do step by step. Now first, add the raw vertical here. It means that the queue from here. I remove 3 only. So let's talk about 3. I put 3 here. Now next, I get generous children. So you can see children of 3 right now. You go back to the here. Get our of 3 right now is 2, 4, 7, 8. Go out of 3. Go to 2. Mean that the hour contain 2, 4, 7, 8. So you can see hour right now. Hour right now you contain here hour 2, 4, 7, 8. So for each of children right now, for each of neighbor, you go to the, you map to the in degree 2. You degree the in degree by 1. Mean that the from 3 you update here is number 2 because you set 1. You subtract 1 because, okay, that is neighbor. So after the update, that is not 0. So you don't do anything. Go to 4. You update, that is equal to 1. Mean that you degree. You 7. You update, that is equal to 2. A, you update, that is equal to 1. And you don't do anything. You just update. You put to the map here again that with the degree -1. And that is not 0. So you don't try to put to the queue. You go next. You remove 1 more 6. You put 6 here. And for 6, you get our degree of 6. Our degree of 6 is 0, 1, 2. Remember, I assume that when getting neighbor, I order by increasing the value 0, 1, 2. Here, here, and here. 0, 1, 2. And for each neighbor, let's say 0. Let's say 0, you update by -1, that is equal to 0. And that because that is 0, so that's why you put 0 to here, to the queue, by this line. Remember, before suppression, that is 1. After suppression, that is 0. Okay, so you can see, even I compare 1, but that is after suppression, that is 0. So that is put, go to net. Here, vertex 1, you -1, that is become 1. Don't do anything. -2, here become 1. Don't do anything. That's all, right? Now netlab, you remove 9. That here is 9. And for 9, you generate the children. You have only one children is 4. So really 4. Only one children. Or one neighbor. Or one adjacent. Number 4. Number you here you subtract 1, that it becomes 0. And because it's 0, so you put number 4 go to the queue. And you go to next. You remove 0. You put 0 here. So 0, you get neighbor of 0. Neighbor of 0 right now here go out from here 1 and 5. 1 and 5. So for 1 you subtract 1 here, that will come to 0. And because it's 0, so you put number 1 here into the queue. And next for number 5, vertex 5. You subtract that it becomes 0, and because it's 0, so you put number 5 here. And you go next for netlab. Netlab you remove, you pop from queue, that is number 4. And number 4, you can see you generate children. Children from 4, that is children from 4, that is 8, only 8. So for number 8, vertex 8, you look up to the table, you subtract 1 from our in degree. That is equal to 0. And because it's 0, you put number 8 into the queue. On netlab, you remove 1, you put to the out result. And for 1, you get the children. Children here are 7. And from 7, you subtract 1. That becomes 1. Don't do anything. Net number 5. 5, you can see children of 5 right now here, nothing, empty. Empty, don't do anything. Now go to number 8. Number 8 right now here, you can see generate children right now. Children of PA, number 8, you can see how many children or neighbor. From 8 you go to 2, and from 8 you go to 7. To 2 and to 7. Let's talk about number 2. 2, you subtract it, become to 0. And because it's 0, you should put 2 here. And for 7, you can see you subtract 70 by 1, that is it comes to 0. And before it's 0, so you have to put 7 to here, to the queue. And go next, remove 2 here. And 2, you can see children of 2. Children of 2 right now here is nothing, so empty. Don't do anything. Children of 7. Right now you go to next. Children 7. Again, number 2. When you generate number 2, that is nothing. Right? Nothing. Number 2 here, generate children. That is nothing because there is no children here. So that is empty. So you go next, remove 7. You put 7 here. And you can see generate children of the 7. No children here. So empty again. And you're done. So you can see right now here how many here you have on of note like that. Let's talk about here. That here is the result you return. Now the queue is empty, right? Queue is empty. So when the queue is empty, you return. You quit and you return turbo. And return turbo, the turbo order right now here, this is turbo order. And you verify right now, is it the order turbo order or not? You verify. You verify how to verify. You can see 3. 3 go to 2, go to 7, go to 2, go to 4, go to 7, go to 8. You just draw a row here. Go to 2, go to 4. Sorry, I want to clear it. Go to 4, go to 7, go to 8. Where I say? Oh, I forgot because when I write number A15A, I have to draw here. I'm missing here. When I remove number A here, I have to put to out after here, middle here. So I had to. Sorry, I have to. I think that is not incorrect. Why no? Because when I remove from the here 1 5, you can see 1 5, and then when you pop from queue, you have to move it to the result. So it must be A. Must be 2. Sorry. Must be A. Must be 2. Must be 7. So you can verify again. 3 to 2. Here, 3 to 2. 3 to 4. 3 to 7. 3 to 7. And 3 to 8. Okay, now 3. Next for 6, you can see verify. 6 to 1, 6 0, 6 to 1, and 6 2. 6 0, 6 1, and 6 2. Now for example 9 to 4. You can see 9 to 4 here. Net 0, 0 go to 1 and 0 go to 5. Go to 1 and go to 5. 0 go to 1. 0 go to 5. Next 4. 4 go to 8. 4 go to 8. Okay. Next 4 go to 8. Next 1. 1 go to 7 only. 1 go to 7 like this. 1 go to 7. Next here is 5. 5 go to nothing, right? Go to nothing. Because here 5 is no children. Number A go to 2 and A go to 7. A go to 2 here and A go to 7. Next for 2. to go no children. 7 also no children. Okay, so that's done. You can check that on of arrow here from left to right. So that is the actually that is the tuple order by breakfast. Traversal. Hello, are you there? Is it clear for you? Hello, are you there?
Yes, teacher.
Is it clear?
Yes.
Any question? Hello. Okay, I want to close this session on the topological order, right? That is exercise. I only plan by hand, and also I show you some code here, right? So let's talk about you have to eliminate by yourself. Any question? If you don't have, I want to close the session today now, right? So I want to close the session. Goodbye. See you next week online.